Hello there, welcome back. We just discussed the notion of an invertible bounded linear transformation between two normed linear spaces, and we had this one example that clearly showed that a bijection in general is not invertible according to this definition because the inverse might not be bounded. Now, that negative example aside for a minute, here is a positive example or result. It's a theorem about the so-called Neumann series. So the Neumann series in a nutshell is just a geometric series for an operator. So let's read the statement. If X is a Banach space and T a bounded linear operator with operator norm strictly less than 1, so in the geometric series that would correspond to your, say, complex number in modulus strictly less than 1. And then the statement is that 1 minus t is invertible, and we have a cute formula for it. So very much like just a geometric series. 1 minus t, its inverse, is 1 plus, and then the infinite series t to the power n. So the nth power indicates the n-fold composition. So you compose t with itself n times, and then you sum up the result. So this equality in particular means that sum there is convergent. Okay, that's the formula, and then to showcase that indeed the inverse is bounded, here is a upper bound for the operator norm of the inverse. So it is less than or equal to 1 divided by 1 minus operator norm of t. Right, and it completely corresponds to the ordinary geometric series that you know from calculus. So that guy here, n0 z to the n, and if you write this as 1 minus z to the power minus 1, you can clearly build the bridge. And this here is valid when z in complex modulus is less than 1. This is the analog. The Neumann series is simply the analog for operators. It's a harmless result, it's easy to prove, and we will use it later on. Okay, so proof. So given that the operator norm is submultiplicative. So remember this. Let me write the word. So when you have two operators, S and T, and you compose them, or two bounded linear transformations, and you compose them so that this composition makes sense, then you can think about the operator norm of the composition or the product. And then we proved in the very first chapter that in general this is not equal to the product of the individual operator norms, but that product gives you an upper bound. So you have this, and that's why it's submultiplicative. Right, so this is what we will use now. Since it is submultiplicative, we find, well, we need to get our hand on this nth power, but okay, you just iteratively use the inequality, you split up one of the t's, then you use this guy, so you have t to the n minus 1 times t, and then you iterate the same procedure on the first factor. Okay, so by the same logic, this gives you the nth power of the operator norm t. Okay, that's what we have, and this works for all natural numbers n. All right, hence the sequence Tn in Lx, remember, this is a Banach space itself, because X is a Banach space from the get-go. So that means this is an absolutely summable sequence, and therefore summable by that theorem that we proved in the last video early on. Right, there was a non-linear space X is complete, aka a Banach space, if and only if every absolutely summable sequence is summable. Yeah, but since here we start with a Banach space X, that means this guy here is Banach space. And since we have an absolutely summable sequence, why is it absolutely summable? Well, because of the geometric series. So the sequence that you're looking at here is, or you can run it from 0 or from n, it doesn't matter, is this guy. And well, that operator norm of t is strictly less than 1. So that series there is convergent because of the ordinary geometric series. Okay, that's why here this sequence is summable. We use S to denote its sum for now. Okay, good. So this is where we use the notion of absolutely summable and summable sequences. Since in operator norm on Lx, now we have to compute that S really is the inverse of 1 minus t, right? So what you do is do a little bit of algebra. So remember, S is the sum of that sequence, so it is not capital N here, small n, from 0 to capital N, and then t to the power small n. Okay, that is the sum. Okay, that's what's written up there. We use S to denote its sum. All right, and what you can do is you can put this limit of obviously all the way out here, because this bracket doesn't depend on capital N. So what you have is, maybe on the next page, you have to look at limit as n goes to infinity. Let's use a bracket, 1 minus t, n from 0 to capital N, tn. Okay, now ignore the limit for a moment and notice that this here inside in the curly brackets, this is again a telescopic sum. Okay, many terms cancel out. You can check for yourself. This is simple algebra. What only survives is 1 minus t to the n plus 1. Okay, and that's why I said in operator norm, because in operator norm t to the n plus 1, it converges to 0, right? So this is equal to, if that converges to 0, then the first term is independent of capital N, so there just survives the identity, right? Because since limit n to infinity, t to the n plus 1 is equal to 0. And how do you prove this? Well, you use again the submultiplicativity and then the fact that the operator norm of t is strictly less than 1. So you have a geometric sequence, z to the n, when n goes to infinity and z is in complex modulus strictly less than 1, that guy goes to 0. Okay, that's what you have here. But here the convergence is an operator norm. Okay, so you have this, and similarly S 1 minus t is equal to the identity. Okay, we conclude, so you have that S is a two-sided inverse. S 1 minus t is the identity and 1 minus ts is the identity. And notice, by the way, that criterion that I used here implicitly about being in a Banach space and absolutely summable sequences being summable, that means in particular that their sum is in the space. So this S automatically is a bounded linear operator. Okay, this is by that theorem about absolutely summable sequences, because the limit element is again in the space, and here this space is bounded linear operators with the operator norm. Okay, so and that's why now we can use the definition about invertibility, because we have an S which is, okay, I haven't actually checked that it's linear, but well, this is again implicitly contained in here, right? So it's bounded linear and it's a two-sided inverse for 1 minus t. Yeah, but that's enough to conclude that S is the inverse of 1 minus t. Okay, let's write it down. Similarly, we therefore conclude, or we conclude, that S is the inverse of 1 minus t, and it is indeed a bounded linear operator. That's how it works. Okay. Finally, we have to show the inequality for the operator norm of S by the triangle inequality and continuity of the norm. Remember, the norm is actually Lipschitz continuous. We have 1 minus t minus 1, an operator norm. So this is limit n going to infinity. Now let's take the 0th term inside the sum. So here the convention is that t to the power 0 is just the identity. Okay, that's the convention. And then what you can do is, by continuity of the norm, you can pull that limit outside. So you have limit n to infinity. Then you have the norm here of a finite sum inside. Then you use the triangle inequality. Limit remains outside, so you have n0 capital N, t to the n, and now you use again the submultiplicativity. So this is less than or equal to limit n infinity, n from 0 to capital N, t to the power small n. Yeah, but now since t in operator norm is strictly less than 1, this is just a geometric series, right? So this guy by the ordinary geometric series is equal to this, and that's the inequality that we claimed. Okay, that's it. So that proves the Neumann series. Good. One last thing now in this section, which is a useful theorem that we will use in the exercises to actually define the Riemann integral in a very different way than how you're used to it, say in calculus, right? There you go through those sums and you know, make the partition finer and finer, and then stuff converges to what you call a Riemann integral. Now here what we will do is we'll use functional analytical techniques, at least in the exercises, and those techniques, they rest upon the next and last theorem in this section that I will discuss. First off, we need a short definition. So let x and y be normed linear spaces. We say a bounded linear transformation from a space x naught to y is densely defined in X if X naught, well, is a dense subspace. Of X. Okay? So the densely defined linear transformations. Now these will be useful because what oftentimes happens in applications is the following, that you start with a bounded linear transformation that makes sense on some densely defined subset, and then you want to, well, sort of continue it in some sense to the full space X, right? And the following theorem guarantees you that you can actually do this. So this is very helpful in applications, and I discuss it now because the upcoming section, this will be Hahn-Banach theorem, is precisely dealing with such theorems, that you start with some, you know, subspace, you have some operators, bounded linear transformations, functionals on them, and then you want to continue them to the whole bigger space. Okay, so this is now the upcoming theorem is the first of actually many such theorems about continuations of bounded linear transformations. Okay, so let's write down the theorem. Theorem BLT, bounded linear transformations. Let X be a NLS. Okay, and by the way, what you should of course keep in mind is that one result in metric and metric space module was about if you have a metric space and it's not complete, then you can sort of, you know, lift it to a complete metric space. And that's also something which is going on here, because this space here, this X naught in the definition of densely defined linear transformations, it might not be a Banach space at all, right? So up front you're working with bounded linear transformation from just a subspace, and then you want to lift it to bounded linear transformation on a Banach space. So that's why also this theorem is useful. Okay, but now enough said. Now I'll write it down. So let X be a non-linear space, not necessarily complete, but Y a Banach space. A Banach space, and T X naught Y densely defined in X. Okay, and what's the statement? Well, there exists continuation with certain properties. Then there exists a unique, okay, S that is defined now on the whole of X mapping to Y, and that S is really a continuation in the following sense, because if you restrict the values of X again to that dense subspace X naught, then S just reproduces the T that you started with. So you have this here for all X and X naught, they match, and you know, when you started with something bounded linear, then you can continue it to something bounded linear, and moreover the operator norms do not change at all in that continuation. All right, and this is also, this last property is very useful, because believe me, computing operator norms in some abstract spaces is quite hard. But it might be easier if you restrict your attention first to some dense, you know, subspace, and then use that theorem and actually realize, well, I can continue the guy to the whole space and the operator norm doesn't change. So that's also a useful fact to have. Okay, let's prove it now. Proof. If, it's actually very easy. Proof, if X naught is a dense subspace, well, what does that mean? Well, it means that every element in capital X you can approximate through a sequence of elements in X naught. Right, that's what it means. Like Q being dense in R, every real number is the limit of sequence of rational numbers. Then for every X in X, we can find a sequence Xn in X naught such that Xn goes to X as n tends to infinity. Okay, given that, well, Txn minus Txm in Y, well, that is the standard trickery now again, playing around with the operator norm that we haven't done now for a while, but here we go again. Right, remember, in general, whenever you have this guy, this is always at most that product of norms there, the first one being the operator norm. This just follows from the definition of the operator norm. So you have this, yeah, but when you have now this in blue there, this just tells you that because this here gets small because you're working with a Cauchy sequence, this means that the image sequence is also Cauchy. Okay, given that this, we conclude that the image sequence, so Txn in Y is Cauchy, and now you realize why you want to have a target normed linear space that is complete, because that thing now has a limit by that assumption. Okay, is Cauchy and thus convergent, say Txn goes to Y as n goes to infinity. All right, note that this element is actually independent, of the sequence Xn for if there exists another sequence, say Xn hat, in X naught such that xn hat also goes to x as n tends to infinity, then, well, txn hat minus txn, this is in y, well, it is at most equal to this guy, minus xn. Yeah, but they both converge to x, so this guy here as n goes to infinity becomes small, and hence txn hat converges to the exact same limit y as txn as n goes to infinity. Okay, for this reason, the map S from x to y with s of x equals to y is well defined. That's how you define your continuation. Okay, through this limit of sequences. It is linear by linearity of t. Remember, linearity implies continuity, or it's actually equivalent. That's what we're dealing with after all. It is linear by, because t is bounded linear, right? That's important. Bounded linear. The boundedness plus the linearity implies the continuity. That's what I want to say. It is linear by linearity of t, and if x is an element in x naught, which is a dense subspace of x, then by the above. So now I have to show that s of x is equal to t of x, right? This was one of the criteria, that if you restrict your elements back to that dense subspace, s just is the same as t. So what do we have? We have that limit as n goes to infinity, txn is equal to y, right? This was the definition, and y was s of x, okay? So, but now remember, xn is a sequence in, I have to write this down, that's important. This is an element in the dense subspace, right? xn is an element in the dense subspace. This x here, this is in the full space x. Yeah, but T is a bounded linear transformation on that dense subspace. So in particular, it's continuous, right? So that fact here, because T is bounded linear from x naught to y, allows me to interchange the evaluation of the evaluation with the limit, right? So you have this. Yeah, but the limit of xn, this was x. So this is equal to t of x. And here it is, right? So when x is in the subspace, the action of t and s is exactly the same. Okay, that's what you wanted. Good. Next, we have to show that statement about the norms, the operator norms. So by continuity of the norm, we have sxy is, okay, so limit n goes to infinity, you can copy paste from the above line. In y, the continuity of the norm allows me to pull that limit out. So this is limit n goes to infinity, txn in y. And then, well, you use that t is bounded linear operator on that x naught thing. So this is in x naught. Then you use the same inequality that I used earlier. So t xn in x, okay. And well, now as n goes to infinity, we remember that xn goes to x. So this is at most t x in x, and this works for all x in x. Okay, comparing the left and the right, this shows two things. It shows that S on one hand is a bounded linear map from x to y, and its operator norm cannot exceed the operator norm of t. Okay. Now how to get the equality there. Yeah, but since we already showed that S is equal to T on the dense subspace, this means the operator norm of S cannot be strictly less than T, right? Because these two maps, they are the same on X0, so you can just evaluate the operator norm on an element of X0, and then they must be the same because the two operators are the same, right? So therefore we must have equality up there. We cannot have strict inequality. But since S is equal to T on X0, we must have the operator norm of S is equal to the operator norm of T. Okay, this was easy. So now one statement remains, and this is about the uniqueness, right? The statement is there exists a unique S with these two properties, right? So if finally, if there are two S and S prime bounded linear from xy that match onto T on X0 for all X in X0, and they have the same operator norms as T, well, and then for every element X in X, we can again choose sequence Xn in the dense subspace that converges to X as n tends to infinity, and we can conclude that S of X minus S prime of X, well, limit again goes out. This time I write it at once. Xn minus S prime Xn. Yeah, but remember, Xn is in X0, and on X0 both S and S prime match onto T, so this is in both cases equal to Txn. Yeah, but this guy is equal to 0 because you subtract the same thing from each other. Okay, so you have this. Okay, and this means that S of X minus S of prime of X is equal to 0 in norm for any X in the space. That means the operator norm of the difference has to be equal to 0, and so these two operators have to be the same. It has uniqueness is established. Okay, that completes the proof of this theorem. Okay, this concludes the current section, and now in the next section we will have many more of these type of continuation theorems. So this will be now the Hahn-Banach theorem in the next section and all its glorious consequences. Okay, I will see you in the next video.